All right. Happy Friday, everybody. A little more enthusiasm for Friday. All right. All right. You can clap or whatever. Friday likes lots of different forms of appreciation. So our goal today is to finish talking about the other parts of the sort of process part of the system call interface, right? So we're sort of done with fork. We finished our journey with fork. We'll do a little bit of review of fork, and then we'll talk about exec, and then wait and exit, which really are our two system calls where the semantics of them are very sort of bound up together, right? You can think of those two system calls as providing a way for processes to exit, right? So exec is change, right? If you remember our whole model of how the system call interface work. Fork is creation, exec is change, and then wait and exit are sort of death, right? They're elimination, right? All right, there's a lot of announcements on the slide, so let me see if I can get to them all. I was looking at the schedule, and the thing is that the semester is going by, right? Like time is passing, probably at the rate it usually does, but it seems a little faster to me this year for some reason. So you have 5 weeks left from today. I guess it's 5 weeks plus whatever's left of today to finish assignment 0 through assignment 2. So that's not an unreasonable amount of time. That's about the amount of time that we would budget for these assignments at other schools that use them. Usually assignment 2, people have about 2 weeks. And we give people about a week for assignment 0 and assignment 1. So it's not an unreasonable amount of time, but it does mean that you guys need to be working on these, right? I postponed the assignment 0 and assignment due date by 1 day. So now it's midnight Friday before spring break, right? Make your travel plans accordingly, I guess. The other thing that is different about this class, and I just want to remind you of, is that because the assignments are cumulative, and also because we're giving you a lot of freedom about how you schedule your time and how you complete them, I'm not going to hand out. Hello. I'm not going to hand out. That was a very dramatic entrance. I like that. I'm not going to distribute assignment 2 solution sets. So, with respect to assignment 2, there's a lot of code to write for assignment 2. You have 2 choices, right? Choice 1, which is preferable, is you can write that code before the deadline, and you can get points for it for assignment 2 and for assignment 3. Your other option is you can wait and then still have to do it anyway, because assignment 3 is not going to work without the stuff you need to do for assignment 2, right? So that choice is up to you. If you want to write that code and get points for it on both assignments, then you should start it soon. If you want to wait and do everything at the end of the semester, then you're not going to get very many points for the other 3 assignments. And really, in order to pass this class, you're going to have to at least do assignment 3, and that's going to mean you're going to have to do all these other things anyway, right? So so I would encourage you guys to get started. On that note, if you still don't have a partner, I think there's a few people in this boat. Please email the core staff as soon as possible, and it's time to start lowering your, it's time to start sort of maybe giving up on a few of those must-haves when it came to finding a partner, right? Like, it's time to get a little less choosy about who you work with because you need to get started, right? So in good news, if you didn't get this memo, the Tuesday recitation is now in Talbert 107, which is great. It's a nice big room. I think most of the graduate students who want to come to recitations can attend at this point. We're also taping the recitations. We have a recitation playlist. It's up on the website. All the videos are there as well. I'm just going to remind you, someone came and asked me today, like, I was gone last week, what should I do? And I was like, watch the video. It's like being there. And we also have a music playlist for the pre-class music, which I don't know, people seem to think that was cool. That's also linked up there. It's not full screen because it's not that important, but it is in the text on the video page. And finally, all this stuff's on the calendar too. So I'm going to be gone on the 26th and 28th of February. I think what I'm going to do is I'm going to assign the lecture videos from last year to watch. Right now, things are sort of fitting in, so I'm pretty much almost giving the same lectures as last year. I don't know what will happen by that point. It really depends on how fast we go, but I'll assign relevant portions from last year's lectures. You guys will be asked to watch them before class, and what Jinghao and Zihei will do will sort of assume that you've seen them and then sort of lead a Q&A session or do some other in-class stuff based on your viewing of those videos, right? So it's sort of like the flipped classroom type thing, but we're just going to do it for a couple of days, all right? Any questions about administrivia stuff? Yeah, Mac.
Kind of an unimportant question. If you've already submitted a music selection, will we be able to submit another one since we didn't know that
Nope, you're done. That was your one choice. Mac wanted to hear Party in the USA, and we played it today. It's a good song. I probably, well, yeah, that was a nice song for before class on Friday. It's a good Friday song. No one requested that for Monday. Any other questions? All right, so last time we talked about fork. Any questions about Wednesday's material before we go on? I'll give you a brief review, right? So today, yeah, we did that. OK. So what happens after fork? The child thread starts executing where? In the mumble. Something more clear. Where does the child thread start executing?
Where it left off, where the parent left off.
Exactly where the parent called fork, right? That's exactly, so the child starts life thinking that it just called fork. Everything else is exactly the same, right? The contents of parent and child memory are what? The same, identical, modulo, maybe some stacks for threads. Both child and parent have, as far as files, after the fork that we've talked about, what files does the child have open, and where are those file pointers? Where are the positions in those files? Same as the parent, right? Same files open at the same position because they're sharing those file handle objects that store the file offset. Right? This is after fork, right? And then there's, so there's one exception to this, to the identicalness between the parent and child. What's the one thing that's different between the parent and the child? Yeah.
Fork returns a different value.
Right. So fork returns twice. It returns the PID of the child to the parent and 0 to the child. Right? OK. So this is all review. Sweet. Pipes. So if I want to establish, as we talked about last time, variety of different things you can do with pipes. Right? What do I use to do that? This is not a trick question. The pipe system call. Right? Create a pipe by calling pipe. That's a nice feature. It's easy to remember. What does pipe create? What are the semantics of the object that's created by pipe? Yeah, Tom. It's like a file, right? It can be read or written to. What happens when I read to? What else does a pipe have? What does a pipe have that's different than a file? If I open a regular file and I open pipe, what's the difference between the semantics of those two calls that's a little bit illustrative about how they work? How many file descriptors does a regular call to open return? How many file descriptors do I get when I call pipe? Two, right? Pipes have two ends, right? If I read from one, I can consume things that were written to the other end. If I write to one end, it appears on the other, right? All right. So just a brief overview of how we created this IPC mechanism using fork and pipe. I create a pipe, I call fork, and then the parent and child close the ends to create a unidirectional way to communicate between the two processes, right? All right. I'm trying to be faster with the review this year. So remember, there were a couple of problems with fork, right? Fork potentially has to copy a lot of state from the parent process. And what's the problem with copying all that state? What frequently happens immediately following fork? Yeah. I'm going to pick on people now. Well, but why don't I need them? What is the child likely to do? Yeah. Wait, I heard an answer. Do something different. In fact, the child is likely to transform itself completely using a system call we're going to talk about today called exec, right? And exec, one of the things exec does is totally destroy the address space that it was run in and load a new address space from an image in a file, right? So fork does all this work, and exec completely destroys all of fork's labors, right? We talked about a couple of different ways to solve this problem, right? One way is to try to optimize the semantics of the existing call. The other way was to create a new call with new semantics. So the vfork call is the addition. It's the way of creating a new call. Is it Griffin?
Yeah.
What does it do? Yeah. It's like fork, but with one difference. So it doesn't copy anything, but then what do I need to do to make sure that things are okay.
It doesn't give the new process an address space. So
Right, but then what has to happen?
oh, it
Load like a template or like a
No, it doesn't actually change the address space immediately, but it will fail under a certain condition. And Tasha?
It will fail if child does anything besides call Jack.
Right, so basically if the child tries to change its address space, we have a problem, because it doesn't have one, right? And so in that case, I fail, right? And basically the only thing the child can do is immediately call exec, right, which creates a new address. What's the way to optimize the existing semantics of fork? I see a lot of forks followed by exec. We talked about a little trick. Oh, I gotta get better with the names so I can pick on people. Let's see. Let's go. The back of the room is always fodder for this. Victoria, what's the way of optimizing the semantics of an existing call to fork? There's a trick, memory management trick that I can play. You want to help her out? It's not clone. It's not clone, it's cow. Who remembers cow? Yeah. Copy on write, right? So I can make a copy of the address space, but I can set up a new address space, and this is tricky. We'll talk about this when we talk about virtual memory. It's not going to make a lot of sense right now. But I can create a new address space in such a way that the address space, I only make copies when the child writes to the address space. So as long as the child and parent are both reading, they can actually use the same address space, right? The content's supposed to be identical. But as soon as either one of them writes to any part of its address space, I need to create a copy so that those writes can be made separate, right? And again, we'll come back to this when we talk about virtual memory. Right now, I'm not sure you guys would even know how this could possibly happen, right? How could I possibly make this happen? But I can't. All right, we looked at using PS tree to look at the process tree on the system. This was my little sort of nice family tree of processes. Most of them started by init. Any questions on fork before we talk about exec? All right, so the rest of the, so we're going to try to do the rest of this today. These other calls are a little simpler, right? So what would happen if I could just run fork? I mean, I could write a computer system with just fork. How would I have to do it? Yeah. Yeah. I could write like this one big program with all these different case statements in it, you know, that fired up every process I could possibly need and like that, but that would be terrible, right? So if I actually want to have the notion of multiple processes, I need something more than fork, right? Because all fork is going to allow me to do is make copies of things, right? When we talk about exec, we're actually talking about a whole group of system calls. If you do sort of man exec or man sysexec, you'll find that there's all sorts of different versions of exec that have different sort of different calling conventions and do things slightly differently. But overall, this entire family of system calls allows processes to change. It allows processes to tell the operating system, I want to be something different. And in order to do that, I have to be able to tell the operating system what I want to be, right? What do I want to look like? And what exec does is it passes a blueprint. You can think of it as a blueprint or a very, very precise specification for how I want my world, my address space to look to the operating system. The operating system parses that and sets up a new address space for this process and then begins executing it, right? So most of the, the programs that, I shouldn't say most, all the, processes that you run have these binary executables located somewhere on the system, right? And we'll talk a little bit about the format of this, right? There's a couple of pieces of information that this blueprint has to have, right? The first thing is the blueprint that I give the operating system in the form of this file, right? How many people have ever just like tried to read through like bin bash or opened it in a text editor or something? What's in there? Yeah, it's binary stuff, right? But I'll show you today there is a way to read what's in there, actually. It's structured data, right? There's a format for it that's common across many Unix-like systems, and we'll look at some tools you can use to do some introspection on that today, right? But there's a couple of things I need to tell the operating system. The first thing is, what should the contents of memory be? When another process talks about what's at a particular address, right? In certain cases, I'm going to tell the operating system what should be there. What's particularly important for a new process to tell the operating system about when we talk about memory, right? There's a lot of things in memory that are stored dynamically, right? That are there because the process has run for a while and it's created some new things and stuff like that. All that dynamic stuff is not part of this executable, right? But what is in bin bash, right? What would have to be in bin bash in order for it to begin executing at all? Yeah. Yeah, the code, right? So all of the code needed to run my program, with a few exceptions, which we'll talk about, but most of the code needed to run my program has to be loaded into my memory when I begin executing, right? And when we talk about virtual memory, we'll talk a little bit about the fact that operating systems, which in another design principle are inherently lazy, don't actually tend to load much of this code right away. They wait until later, but they know where to get the code and they know where the process wants the code to be, right? So when I start running, one of the most important things I tell the operating system is, here's all my code, right? Here's my compiled sort of binary image, and here's where to put it. And then what's the second thing I need to tell the operating system if I'm actually going to begin executing? This is a reading comprehension question. Who wants easy points? Yeah. Where to start executing, right? So because the operating system is going to sort of pull me off to the side, set up all this stuff in my address space, and then it needs to know essentially the entry point for my program. How many people, so if you've written programs in C or C++ or other sort of what are now low-level languages at this point, what is that, as a C programmer, kind of what does that correspond to? Main, right? It turns out it's actually not main. There's actually stuff that the C library, if you use the C library, there's some stuff that it runs before you get to main, right? But from a programming perspective, main is the first set of instructions that you write as a program, right? There's some other things that happen beforehand, but main is pretty close to being what it is, right? All right, so Linux and other sort of Unix-like systems use a specific format for storing this information, right? It's called ELF. Has anyone ever heard of an ELF format executable? OK. Some of the sort of like hacker types here. It's the executable and linkable format. And this is important, right? Because a lot of times, a lot of the code that you run on your system isn't compiled on your system. It's compiled somewhere else. And so the output of the compilation is this file, right, which I can move around as long as certain constraints are met. And if this wasn't consistent, then it's possible that other systems wouldn't know how to interpret the contents of this file, right? I give you this file, but the system says, I don't know. To me, this is all just a bunch of binary stuff. I don't know what to do with it, right? All right, so this is cool. You guys should play around with this on your VirtualBox, or probably also, I don't know if Timberlake has these tools installed. As we go through the semester, if you guys, if you find stuff like this that is lacking, particularly about some of the instructional environments that you guys use, you should let me know, and then or you could just email the CSE consult people and ask them. Because these are pretty cool tools for people to be able to have at their disposal. And they're harmless, basically. All right, so this program is called readelf, right? And as it probably sounds like, it reads and prints information about the contents of an ELF file executable, all right? So what this command will tell us is that this is an ELF file. It's an executable file. What other types of ELF files might there be? A file that's an ELF executable is, by its very nature, executable, right? But ELF is the executable and linkable format. So what other kind of ELF file could I have? Yeah, I could have a shared library. Shared libraries actually also use this format with probably a lot of different bells and whistles to it. But we're going to focus on executables for this example. So what's this, right? It says entry point, and then there's this hex address. Entry point. Yeah, that's the point where the process, that's the location of the first instruction that the process will run when it begins to execute, right? So once the operating system has loaded this file into memory and put things where the file wants them, it will start the first thread of this process at this particular entry point, right? This gives you some more information about the file. And then here's some information about what are called program headers. These are parts of the file that map to specific areas of memory within the process's address space. So this is, I can't remember what some of these mean, actually. So So here's some flags. These look a lot like the flags we see in other places, right? So this tells us something about what's potentially in here, right? So this is p header. Here's an offset, a virtual address, physical address. So what this, I won't bore you with too many of these details, although I think they're kind of interesting. What this actually says is here's the offset into the file, and here's the location in the process's virtual address space where this stuff's going to go, right? So you can think of the file as the address space of the process, which is potentially quite large, compressed down into a file, right? And all the spaces between different parts of the process's address space have been eliminated, and to make one sort of contiguous block of stuff, right? All right, so, and then there's this interesting stuff here. So remember I said before that not all of the code that I need to run bash is actually in bin bash. Where is the other stuff? We talked maybe a week ago about other types of code that an executable like bash might use. Yeah, shared libraries, right? So those shared libraries, by their definition, are not, if they're dynamically loaded libraries, they're not part of bash, right? You can create executables on these systems where all the code is located in the same executable, right? Those are sometimes called statically compiled, right? The problem with those, of course, is when people fix things in these libraries that you're using, you don't actually get those fixes until you recompile the whole program, right? So what's interesting here is that this is saying I'm requesting program interpreter, and then it gives this interesting looking path, right? And so the first time I ran this, I was like, oh, that's kind of cool. I wonder what that is. So I ran it. And this is one of the longer, sort of more interesting help messages I've ever seen on a program I've run on my computer. What I like is it says, chances are you did not intend to run this program, right? But I actually did intend to run it. But anyway, so this turns out is a helper program that's used to help dynamically linked executables load stuff from shared libraries into their address space, right? So you don't really need to know how this works, but this is pretty interesting. All right. So one of the things that I can do, yeah, sorry.
So exec is expecting a file in ELF format?
Yep. Yeah, sorry, I should have said that. One of the arguments to exec, and you will get very familiar with these arguments as you implement exec for assignment 2, is the program, the file to load the ELF data from. Luckily for you guys don't have to write that code. It's already written for you. Parsing ELF executables, at least simple ELF executable parsing, is not particularly interesting. So we don't ask you to do that for the assignment, but we ask you to do other things. Did I answer your question? Yeah. One of the other things is pass arguments, right? So one of the things I frequently might want to do when I run a program, when I call exec, is actually allow the parent, it's almost like making a function call, to pass arguments or information to its child, right? And the way this is done is by passing arguments to the exec system call. There's a bunch of different flavors of exec that do this slightly differently. But in all cases, what has to happen is the parent, if you think about it, sorry, I shouldn't say parent. Okay, let me back up. There are ways for me to sort of to pass arguments to my new future self, right? Because there is no new process being created here. I'm going to change, right? But when I change, I'm allowed to sort of pass some arguments to my new self, right? What makes this a little bit interesting is that what's going to happen to my original address space, right? So I had a bunch of stuff in memory. I call exec. Assuming the call to exec completes, what happened to all of that memory that I was using before? It's freed up. It's more dramatic than that. Where are the contents of my old? It's gone, right? It's history. You know, I'm a completely new process, right? I don't maybe even remember what I was before, right? I'm just bash now. I might have been in it before, but now I am bash, and I never knew I was in it in the first place, right? Except for the fact that the exec allows me to pass some information through the system call. And this information has to be copied into the kernel, right? And then held there while I set up the new address space, and then placed in the address space at a particular location. Again, C programmers in the audience. So the entry point is main. What are these arguments? How do you guys see these arguments when you guys write C code? So arguments from the, well, they start on the command line, right? But where do they end up? Yeah, main takes arguments, right? Takes argc and argv. Argv is an array of arguments. Now those arguments started on the command line, but how did bash get them to the program? Through exec, right? There's no magic here, right? Those arguments were collected by your shell, and they were used as part of the arguments to the program that you ran, right? And the way that they got there was that at some point someone called exec to run that program that you asked to run, and those arguments were passed into exec through the kernel, right? So exec is also exec is also interesting, right? So if you think about like the preservation of return calls, right? So fork creates a new return, right? It returns twice. Exec, on the other hand, never returns, right? Because what does it mean to return from exec? If exec succeeds, then there's nothing to return to, right? Does that make sense? Because the process that called exec is gone, right? Exec will return if it fails, right? If it fails, it means there's no actual new me. I just need to try harder again to become something new, right? I screwed up. All right. So, to sort of illustrate this a little bit more clearly, let's say I'm running bin true. I make a request to the kernel to run bin true. I pass some arguments to bin true. I actually wouldn't pass any arguments to bin true. Believe it or not, bin true doesn't take any arguments. It just returns OK, right? But I actually don't think bin true would mind if you passed it arguments. So I can pass it arguments, right? Just not going to do anything with them, right? Now I load my bin true executable and parse it as an ELF binary. And again, what's in this file is some description of how bin true wants its address space to look when it begins executing, right? So I'm almost done. I've got this executable that's ready to go. The file also contains the entry point. But what's the last missing piece I need to do here before I could run this new program? Again, the address space is almost right, except for one. What's that? No, the stack pointer will be initialized properly when I start running. Yeah.
Get rid of the address space of the caller.
I do need to do that. What's hard about getting rid of the address space of the caller in exec? What do I need to make sure? What do I need to make sure doesn't happen before I get rid of the address space of the caller? Yeah, I have enough memory to do this. Yeah. Well, let's put it this way. Once I get rid of the address space of the parent, from the caller, what can I not do? Go back. So what can I not do in exec? What can exec not do at that point? Can't fail, right? Anything I do that might fail, I have to do before I get rid of the old address space. Because if I fail, let's say the file doesn't exist. Whoops. I've got nowhere to go home and tell that to because that memory's gone. Whoops. It's like, oh, well, you asked to change and I just decided to kill you instead, right? Like, that's not very nice. So it violates the semantics of the call, right? What I need to do here, however, going back to the question, is I need to get the arguments there, right? So I'm going to, probably what I would do is I put the arguments into the new address space and then replace the address space of the call, right? If you were watching this carefully, what thing did exec and not necessarily do? So I changed a lot of stuff, right? I changed this process into a completely new process. Gave it new identity, new code to run, a new set of arguments. But what did I not change? I didn't necessarily change the file table, right? The file table, now there are variants of exec that will allow you to reinitialize the file table as part of the call. So I can if I want to, right? But why would I want a version of exec that allows me to not modify the file table? Yeah. Remember, I did all of this work in fork to preserve the file table and create these shared file handle objects. But most of the time, I do that so I can establish communication between two different processes, right? So if I call fork, and then my child calls exec to run a new program, and I start piping data to it, if exec replaced the file table by default, then we wouldn't have any sort of shared file handles anymore, right? So exactly, right? So I don't want to undo all of this hard work that fork did, right? All right, so I told you at one point that we were in the process of like writing a little sort of simple shell, and simple shells can actually be quite simple. So this is not this is not working code, right? I'm not even sure this would compile, but this is more or less at a very high conceptual level what your shell is doing, right? And this shell doesn't handle pipes, it doesn't handle all sorts of interesting things, but it would sort of work, right? So what do? Basically, I read a line from the terminal. Once you type me a line, and then I call fork. And now I've got two copies of me, right? So as soon as I'm here, there are two me's, and one of them is going to exec the line that you gave me, right? And there's all sorts of problems with this, right? It's not handling arguments correctly. What's another problem? So the child, let's say I'm just using this to run, like the 2 or 3 programs on your computer that don't take any arguments, right? And never take arguments, right? Then this would work. But what's the problem? So the child comes in here and calls exec. So it's now a completely new process, and it runs a little bit. Maybe it interacts with you, maybe it doesn't. What's the parent doing? No, what is the parent doing? It's right up here. It's trying to read from the terminal, right? So let's say the child is trying to read from the terminal. Now I have a problem, right? So there's one last piece of this that we're going to finish up today, which is in many cases, I need some way for the parent to communicate with the child. And a very sort of classic design pattern is I want some information about when my child has exited, right? I want to allow one program to run another program and wait for the result of the output, right? This is very much like making a function call in languages that you're used to. Here we're doing it across process boundaries, right? And so we use the process system call interface to do this. So now I have a way to create a new process, and I can replace the content of a process, so I'm almost finished. What I need to be able to do now is sort of recover something about the output of that process, and also potentially wait so that I can wait until that process completes, right? Right, so we talked about this already. Yeah, we want to make sure that, OK. All right, so there's two halves to this, right? So the parent may want to be able to wait for the child, or at least find out some information about the child's status. Is my child alive? Is it still running? What is it doing? Did it move to somewhere, like some other state, Some of you guys may have similar issues with your parents, right? They may be performing a blocking wait call, right? You should tell them to do a non-blocking wait call, right? Anyway, that's a bad computer science joke. So, as you would expect, processes essentially control the moment where they're going to stop executing by calling exit, right? And this is entirely today talking about sort of graceful exit, right? Exit when you meant to, right? There's plenty of things, and we'll talk about this more next week, that processes can do that will cause the operating system to exit them, right? If I give the process bad memory to use, or make a system call with arguments that are all bogus, the operating system may choose to exit me, to end the process. But when a process is finished, it calls exit, right? And one of the ways that we enable IPC, if you remember like a week ago, is that there's a small amount of information that I can pass from the child back to the parent when I call exit, right? And we call that a return code, just an int, a small piece of information. And what happens to this exit code is that it's retrieved by a call to wait, right? So my child runs, it does some stuff, and then when it's finished, it has one little int worth of chance to tell me something about what happened to it, right? And it turns out that one of the reasons why this amount of information is so small is that this information is potentially preserved by the kernel for a long time, actually, until the parent retrieves it, all right? So, and the way that the parent gets a hold of this exit code is by calling a function called wait, right? So remember we talked about these two are inherently paired, right? Wait will, in most cases, well, I shouldn't say that. There's a blocking version of wait that will return when my child calls exit and will not return until it calls exit, right? So if I want to wait until my child exits, I make a wait call. And when my child exits, that wait call returns. And when that wait call returns, it gives me access to the child's exit code, right? And that can give me some small amount of information about what happened to the child. And yeah, and this set of calls just doesn't like fit into the lifecycle metaphor so well. And again, these two calls essentially remove all traces of a process from the system. So if I call wait, let's say I make a blocking call to wait, what will happen? Once that call completes, will there be any trace of the process that I'm waiting for? No, because what will have happened? What causes wait to finish? Exit. So again, wait and exit together. Once the parent has called wait and the child has called exit, no trace of the child left in the system except for the exit code that the parent still has, right? But the operating system has no information left about the child, right? What happens if the child exits but the parent hasn't called wait? This can happen. Sometimes parents choose not to wait for their child. Not immediately, right? So it turns out that the operating system maintains this tiny amount of information, that return code we talked about, just an int, until the parent calls wait, right? And so if my child exits and I haven't called wait, then the child is completely cleaned up. Its address space is removed. It's not running anymore. But the operating system still has that small amount of information about the child, right? And processes that are in this state we call zombies, right? They're the almost dead, right? Like they are technically dead. They are not living, but there is this tiny amount of information left about them, right? How many people have seen this kind of behavior when you've used a shell? Can someone describe what that looks like? So first of all, how does a normal shell use a blocking wait? Tell me how a normal shell uses a blocking wait. It's part of its normal sort of execution loop. Yeah. No, let's try I'm just gonna run bin true, right? Remember, it's gonna grab the info from the command line. It's going to fork, so there's a new process to replace. It's going to run that, and then what's the parent going to do? Yeah.
It will bring you back to the command line once the process finishes.
Yeah, so what I do is I call wait on that child, and until the child exits, I don't consume more input, right? So when you run something and the shell's not printing anything, the shell is waiting for its child to exit, right? What can you do to cause the shell to not wait for a child to exit? Yeah. Yeah, so if I put an ampersand at the end of a command line, I can run a command in the background, right? So what happens when you do that? How many people have done this? OK. So the shell returns immediately, right? And gives you a prompt, right? And then let's say that this background process goes on running for a while and then eventually exits. When does the shell tell you about it? Yeah. Sorry. So I run. So let's say I run something in the background, and it takes a minute or two to finish. I go get coffee. I go back to my shell. Does the shell tell me that the background task is finished? When does it tell me? Well, I don't even have to run another command. What can I do? Just hit enter, right? And then it will tell me. So what do you think the shell is doing, right? So there are two versions of wait, right? There's a wait where I can block until the process completes, and that's used by the shell when you run something directly in the shell. And then there's this other kind of wait where I can essentially ask the operating system, hey, what about that child? How's he doing? And the operating system might say, oh, he's still alive. And I'm like, OK, sure. Like, I'll check on him again later, right? So it's a non-blocking wait. So when is the shell running a non-blocking wait? So again, if I run something in the background, walk away, and that background task ends, the shell doesn't tell me immediately. But when does it tell me? Yeah.
So it'll call a non-blocking wait
Not periodically. It does do it periodically, but what it's triggered by. What's that? Yeah, it's triggered by its normal sort of input processing loop, right? So even if I just hit enter, right, it's like, oh, I get to run again, and I'll check on all those old children, right? And if one of them's died, it will finally tell you, right? The other thing about wait and exit that is fun from an operating system design perspective, and I'll just mention this in the aside, is that this creates sort of a cool synchronization problem for you guys to solve for assignment 2, right? Because the wait and exit calls by the child and parent may happen almost at the same time. Remember, these are 2 separate processes, so they're being scheduled completely separately. And if you have a machine with more than 1 core on it, how many people have a machine like that? Yeah, me too. Some people have smartphones like that now, right? Then they actually might be running simultaneously. So, and if those calls to wait and exit interleave in the kernel, you still have to make sure that all traces of the process are removed and the parent gets the exit code properly. So this is just a little bit of fun for you guys to look forward to in the next 5 weeks, right? So what happens if a process is, so here's one corner case we haven't talked about, right? So what happens if a process's parent exits before it does? This is kind of like, maybe I shouldn't use this sort of like birth, life, death, afterlife sort of model, because it just occurred to me that one of the sad things about computer systems is children almost always die before their parents, right? It's not how it's supposed to be, right? It's supposed to be the other way. So let's say that the parent dies first, which is, more normal. What complication does this create? Yeah.
Finish the process, but then leave its exit status.
Yeah, because if my semantics of wait and exit are the process's parent gets to collect its exit codes, again, there's no parent, right? So what are some ways of potentially solving this problem, right? So, well, I'll just tell you, right? So what happens is there's a variety of different design solutions here, right? What could you do? What are some things you could do? The process's parent exits, so what could I do? What? I could kill all the children. I like that. So actually, it turns, but see, this isn't so weird. How many people have ever run something from the shell and then exited the shell and seen that other process exit, right? So it turns out, I think this is important to point out, this is not a result of the operating system, right? What actually happens is when a process's parent exits, all of the children of that parent receive a signal, right? That signal is called sigchild, it turns out, right? Some processes choose to handle sigchild by exiting, right? But that's not a requirement. So, and again, so this is not something that's being enforced by the operating system. The operating system notifies children when their parent exits, and sometimes children will choose to exit themselves, but there's no requirement, right? So, some of you guys have probably had this frustrating experience where you run some GUI application from your terminal, and then you close the terminal, and the GUI application closes, right? And you're like, how do we get away with this? And there is a way to fix that, right? And some GUI applications just don't close, right? Because that's not necessarily the right thing to do. On a lot of systems, what happens is this orphaned process. So there's a variety of different ways to do it. You could just set the process's parent to be none, right? And then when the process exits, you just don't save its exit code, right? You could assign it to the parent's parent, right? Like give it to its grandparents, basically. What a lot of systems do is they assign this orphan process to init, right? So init is now sort of like the surrogate parent of all the children on the system that don't have parents. And init one of the things init does is sits in a loop and just retrieves exit codes, right? Because again, I don't want these exit codes for these zombie processes to stick around for too long. And so I make sure that there's a process on the system that's in charge of just sort of reaping them, right? Because at this point, nobody cares about this child anymore, right? Like init doesn't care. It is like, I don't care if you return 7, right? I just don't care. I'm just going to grab your return code and throw it out, right? Right, so this is the child. Yeah, so on bash, there's this, so this is great bash sort of built-in command called disown, right? And disown will essentially cause bash to, maybe it's, I'm trying to, oh, okay, sorry. So I actually got this backwards. So sigchild is set by the child to the parent, allowing it to get its child's exit status. And sometimes the process can automatically have its children read. On bash, if you use this built-in, this causes the signal not to be sent, right? So if you want, there's also a command called no hup that'll cause the same behavior. All right. So again, we talked about these two types of wait. I have both a blocking and a non-blocking wait call, so I can retrieve exit statuses either synchronously or non-synchronously. So let's go back to our shell, right? So we're almost done here. So we've made this small change, right, where rather than returning to the top of the loop and competing with the child for input, the parent is going to call wait, right? And this is, by default, a blocking call. I think you still have to pass a flag to wait to get it to be non-blocking. And so this command will finish once the child has finished executing, and now I can go back to the top of the loop and keep going. All right, so, but we've only used 3 of our 4 process-related system calls here. So where's exit? So this is potentially a perfectly valid C program, maybe. You'd have to provide implementation of read line. I don't think that's a standard function. I just made it up because it sounds like what it does. But where is exit here? What's that? Right, OK. So the child process definitely needs to call exit, but where does the parent call exit? Where does this code call exit? Yeah. No, I mean, again, I could throw this into main and run it. And I mean, clearly I may not need an exit here because I have a while one loop, right? But let's say that I could process an exit command from the command line and allow the shell to exit. What calls exit? Yeah.
The return 0, return 0.
Yeah, so it turns out that the return code of main gets passed to exit. And if you don't call return from main, I think well, first of all, you have to, right? Because the call signature of main is an int, right? So that int that you return from main actually gets passed to exit. Who does that? No, not the operating system is the thing that is going to be called by exit, right? What's that? No, something needs to call exit. What calls exit? Yeah.
Whatever the C library calls main.
Yeah, exactly. So if you it turns out if you look at the C library carefully, you can find where it calls main, and then you can find where it takes the return code from main and calls exit, right? So that's all that little wrapper does. Well, it probably does some other things, but basically calls your main function. When your main function completes, it calls exit to make sure that exit call gets made. Yeah.
But you can bypass that by calling exit yourself.
I think you can. Well, yeah, you can, right? Because in many cases, when would you normally want to call exit yourself? When's a very common case to call exit manually rather than letting the C library do it? Yeah, I guess you could just call return, but sometimes you're deep inside another function and you just want things to exit immediately, right? So if you've got some function that's called another function and then it hits some sort of error, you may just want to call exit because you're like, I can't deal with this, right? So that short circuits the whole logic, and that will just shut down the program immediately, right? It doesn't need to return all the way up the stack through main, right? You can return, 1 from main, and that will return an error code to the parent, but you can also just call exit at any point in the program, and again, that will just terminate things immediately, right? All right, I think so yeah, this is one last little bit, a thing I just want to point out because people do get confused by this, right? So how many people have used Erno before in the C library? Oh man, Erno. Too bad. Well, anyways, I just want to, so a lot of what you actually use, right? So how many people have called read or write or open and close in C programs, C++ programs, all right? Those functions are not system calls. Those functions are provided by the C library, and they wrap system calls, right? They usually don't do very much. A lot of times, they're automatically generated, right? There's a little script that writes the stub code for all of the system calls, right? The system calls in many systems are prefixed by sys, right? So open is the C library open call. Open calls sysopen internally, right? And one of the things that many of these functions do when they return is they set this Erno variable, right? Because frequently, especially when there's an error condition, the calling signature of open is different than sysopen, Right? Sysopen returns a lot of different errors, and open, I think, only returns -1 if it doesn't work. Right? And then if you're a C programmer, you're supposed to check error no for more information. Right? So it turned out that sysopen returned some non-zero number that indicated what went wrong. The C library set that and then returned a different value than what was returned by the system. Right? So it's just important to know that all these things we've been talking about, open, close, read, write, pipe, they're all wrappers to these underlying system calls. Right? Very simple ones, but they're still there. All right, so now we've done this sort of like top-down look at the operating system, or at least a portion of the system call interface, from the perspective of a user program. Now we're going to sort of start getting into the guts of how this stuff actually works in the kernel, right? And the first thing we're going to talk about, sort of the next unit of this class, is our threads, right? So threads abstract the CPU. Next week we'll talk about interrupts and kernel privilege and some fun stuff, and we'll go on from there to talk about scheduling and other things, right? So I will see you on Monday. Have a great weekend.